This video we're going to talk about the thermal considerations of internal flow. So here we have a pipe entering at some uniform temperature T, and if the pipe is at a different temperature Ts than the incoming fluid, a thermal boundary layer forms as the fluid enters the pipe. Note that we're looking at the situation where the pipe surface is hotter than the fluid. You can see in that dark gray area where the thermal boundary layer is, the temperature profile is changing with respect to R. In the light gray area towards the center of the pipe, where the effect of the pipe's surface temperature has not yet been felt, you can see that the temperature profile does not change with respect to R. Of course, the thermal boundary layer is developing around the circumference of the pipe, and at some length down the pipe, there's convergence, and that marks the boundary of the thermally developing region. So we say that flow is fully developed if the ratio of Ts minus T over Ts minus Tm is not changing with respect to X. T as a function of R and X is the fluid temperature at some location R and X. Tm is the mean fluid temperature at some location X. Ts is the pipe surface temperature at some location X. And the condition of thermally fully developed flow, you see, is a dimensionless temperature difference. Exactly what that temperature profile will look like will depend on the condition at the surface of the pipe. We'll consider two cases, constant surface temperature and constant heat flux, which will result in different temperature profiles. So here we have the case of a constant surface temperature. Keep in mind that unlike the velocity profile in fully developed flow, the temperature profile will most certainly be a function of X. So in this case, we have a constant surface temperature along the pipe. So you'd expect the fluid temperature to come closer and closer to that surface temperature as the fluid flows along. So the temperature profile is going to change as we move down the length of the plate, and the mean temperature of the fluid is going to increase. Just like the hydrodynamic entrance length X subscript FDH was dependent on whether the flow was laminar or turbulent, the thermal entrance length X subscript FDT also depends on whether or not the flow is laminar or turbulent. So if the flow is considered to be laminar, which would be the case if your Reynolds number was less than 2300, the thermal entrance length is 1/20th the Reynolds number times the Prandtl number times the diameter. Note that this looks really similar to the equation for the hydrodynamic entrance length. So if the Prandtl number is larger than 1, the hydrodynamic entrance length will be smaller than the thermal entrance length. If the Reynolds number is larger than 2300 and the flow is turbulent, the thermal entrance length is 10 diameters. And you will recall that this is the same as the hydrodynamic entrance length for turbulent flow. So we are fully developed if the derivative of this dimensionless temperature is 0. So let's take the derivative of it with respect to R at R0, right at the pipe surface. Do note that all of these temperatures are constants in the radial direction, but not necessarily in the X direction. The surface temperature is not a function of R, but of course the temperature of the fluid is. And if the fluid is fully developed thermally, this dimensionless temperature is not a function of X. So the derivative of that dimensionless temperature with respect to R is not a function of X either. So we can say that this entire equation is independent of X. Think about flow in a pipe. At the pipe wall, the velocity is 0. So heat transfer is by conduction. Therefore, at the surface, the heat flux by conduction and convection are the same. So applying both Fourier's law and Newton's law of cooling, we get a relationship for the partial derivative of the fluid temperature with respect to R evaluated at the pipe surface. This quantity is independent of X, and so we can say that H divided by K is independent of X. And so if we take K to be a constant, H is independent of X in the fully developed region. So while H decreases in the thermal entrance region, it stays constant once the flow is fully thermally developed. In the next video, we'll talk about energy balances and those two special cases, constant surface temperature and constant surface heat flux in a pipe. So thank you for watching. Let me know if you have any questions.